All right, here we go. Unit 1, Day 2. Unit 1, Day 2 is called Graphs Can Solve Equations 2. What I'm about to show you is one of the coolest and most important math hacks you're ever going to see. It is going to be like magic powers. It's going to allow you to solve all kinds of equations that would normally be way ahead of where we are at currently in math. It's a trick that's always going to work when you have an equation that you're trying to find solutions to, meaning values that make the statement a true statement. So if we look at this example that we're going to start off with, negative the absolute value of x minus 2 plus 3 equals negative 2. When I say solve for x, I'm just looking for what values of x make that a true statement. And the technique we learned for solving absolute value equations is to get the absolute value equation by itself. We'll subtract 3 from both sides. That'll leave us with negative the absolute value of x minus 2 equals negative 5. We'll go ahead and I want to get rid of this negative sign. I like to do that by multiplying both sides by negative 1. Since a negative times a negative is a positive, that leaves us with the regular absolute value of x minus 2 equals positive 5. Here we learned how absolute values work. Either x minus 2 is already 5, either x minus 2 is already 5 and the absolute value doesn't really do anything, or x minus 2, if it was equal to negative 5, the absolute value would turn it positive. So on the left-hand side, we'll add 2 to both sides. That'll give us a final solution here of x equals 7, right? 7 minus 2 is 5, so that works. On the right-hand side, when we add 2 to both sides, negative 5 plus 2 is negative 3. So we'd have x equals negative 3. Now you do want to always go back and check that these work. So just kind of talking through it quick, solution means makes it true. So if we take that 7 and we plug it in, 7 minus 2 is 5. The absolute value keeps it 5. The negative makes it a negative 5. Plus 3 is negative 2. So my 7 works. Really quickly, let's check. Does the negative 3 work? Negative 3 minus 2 is negative 5. So the absolute value will make it positive 5. See how that split is making the same thing happen in both cases. Negative 5 plus 3 is negative 2. So both of those work, we're good to go. This is a medium level equation. It's, not an easy one for sure. But they get harder than this. You can get absolute values on both sides. And we could have all kinds of crazy things going on. So what I'm going to show you is another way of solving these types of equations just using graphs. We'll do it by hand first, but this will also work on your graphing calculator. It's a really powerful technique to use, whether you're doing it on a STAR exam, your ACT. It's one of the most powerful, useful things that you'll see in this whole class. So here's what we're going to do. I want you to focus on the why here, right? Focus on the why this works as I'm explaining it. Step 1, I'm going to treat each side of the equation as its own equation that is equal to y. So by that I mean I'm going to start with negative x minus 2 plus 3. I'm going to say here's one equation, y equals negative the absolute value of x minus 2 plus 3. And then the right-hand side of my equation is just that negative 2. So my right-hand equation is just y equals negative 2. Now, this is not a lesson on graphing absolute value functions, so I'm going to go through this pretty quickly. If I were to graph this absolute value function by hand, the first thing I think of is where the vertex is. The vertex is going to be located at an x value that makes the absolute value 0. So x minus 2, what value of x would make that 0? That would be 2. So 2, and then if I were to plug that 2 back in, this whole portion would be 0, and we'd just be left with y equals 3. So I know my graph has a vertex here of 2, 3. Now, in the rest of the unit, we're going to work on doing these really quickly. You know right now how to make a table of values, right? You would check what happens if we've got x and y. What happens 2 places to the left, so like at 0 and 1. At the vertex we already know is 3, and then 2 places beyond, say 3 and 4. So say we had, if we plugged in 0, we'd have the absolute value of negative 2, that's positive 2, negative 2 plus 3, we'd have 1. And so long story short, you could go through, you could plug all of these values in, and you could wind up with a graph here. You'd have 1, you have 0, 1, 1, 2, 2, 3, back down to 3, 2, and then 4, 1, giving us that V shape that we're used to. Now, if you're doing this by hand, an important thing to do, I'm going to just keep plotting these slope of 1 type points, slope of 1 and negative 1, because I want to make sure that I'm able to see the intersection points on this graph. So I'm drawing this really carefully. I'm going to draw through all, it's so hard to do. I'm going to draw through all of these points here. That's not terrible. I'm going to draw through all of these points here. Missed a little bit there, but we'll adjust for it. Those are all of the solutions to y equals negative x minus 2 plus 3. You pick any point on that graph, it's a solution. So if I picked like this one here, if I picked 8, negative 3, if I go ahead and I plug in 8 for x, I'd have 8 minus 2 is 6. Negative 6 plus 3, yeah, that's negative 3. So graphs tell you solutions, which means if we graph this second equation, if we graph y equals negative 2, that is a flat line. It's a flat line showing, oh, y equals negative 2 here, and here, and here, and here. These are all the places where y equals negative 2 is a true statement. So I can graph this line here like so. And it turns out that we have 2 points in common. When you plug in 7, our output is negative 2. When you plug in negative 3, our output is negative 2. So let's think about what this means for a second. We have just found by graphing the two x values, negative 3 and positive 7, that when you plug them in, you get out negative 2. That's exactly how we checked our answer of the first problem. We found the x values that when we plugged them into the left-hand side gave us negative 2. So we have found these solutions by graphing. The solutions are x equals, and I'll do this in the way Delta Math does it, the solution set 7 and negative, sorry, not negative 2, 7 and negative 3. Another way to say this is x equals 7 or negative 3. The key point here to remember is that your solutions are the inputs. They're the inputs that make this a true statement, so you're looking for the x values. Test 1, we already tested these back in our original equation, so we know they work. I'm going to skip past those for the sake of time. The reason this is so useful is that we can get equations that are actually quite a bit harder than what we've done before. What's tricky about this one is that there's an x variable on the other side of the equation. And it's going to turn out that this actually can often give us false solutions. So let's quickly go through and see what this looks like. If we subtracted 4 from both sides, we'd have 3x minus 10 is equal to 4x minus 4. Okay, I've isolated the absolute value, so I could split into two options. I could split into option number 1, and that would be that 3x minus 10 is already equal to 4x minus 4. Or I could do option 2, and that's that 3x minus 10 is equal to, we have to make this whole thing negative, so we have to change the signs on everything. Negative 4x minus 4, which would be equal to negative 4x plus 4. So you can tell this is already getting trickier. Solving these really quickly here, I would take 3x away from both sides. That would leave me with negative 10 is equal to x minus 4. I'd add 4 to both sides, and I'd get negative 6 is equal to x. So that's one potential solution. Working the other way, if I added 4x to both sides, and I got 7x minus 10 is equal to 4, and I went ahead and I added 10 to both sides. 7x is equal to 14, and x is equal to 2. These look like these are my two solutions, but let's see what happens when we test them. So it looks like x equals -6 or +2. Always got to check. So let's check 2. Plug in 2 back here. Let's see. We have 3 times 2 is 6, minus 10 is -4. The absolute value makes it +4. 4 plus 4 is 8. So on the left-hand side, we have 8. On the right-hand side, 4 times 2 is 8. Okay, so 2 appears to work. This looks like a good solution here. But what happens when we try -6? -6 times 3 is -18. Minus 10 is -28. The absolute value turns it into +28. Plus 4 is +32, which is weird because 4 times -6 on the other side is -24. So it turns out this is a false solution. It happens because when we split the absolute value, there's some funkiness that goes on here when you split this up into two sides, and you're changing the value of the sign of the variable that's on the other side. So you have to check these solutions. One great way to check that, or to do this problem quickly, is to look at a graph. And so I look at the graph of my functions. I've got the right-hand side here. So remember my right-hand side. This is 3x, the absolute value of 3x minus 10 plus 4. That is this red graph. And the blue graph is 4x. And as you can see, there's actually only one solution. The only solution is 2, 4. And so if I were able to graph this function, I would say x is equal to 2, only solution, done. Because when I graph the left and the right-hand sides, the only input that they give the same output for, the only thing I can put in a box that represents the left-hand side and put in a box that represents the right-hand side, and they give me the same number out, the only one is 2. So that's how you can solve